In this video, I will give you an overview of the main methods that are currently used for solving integer programs. These methods are based on two algorithmic principles, which are called the branch and bound method and the cutting plane method. Both of these principles are based on very simple ideas, and both are at the heart of state-of-the-art software to solve integer programs. To discuss these methods, let's start from a mixed integer linear set and the corresponding mixed integer linear program. Our mixed integer linear set is denoted as always by S, and as always it is the set of points x and y in Zn plus times Rp plus, such that ax plus gy less than or equal to b. The corresponding mixed integer linear program is the problem of maximizing the linear function cx plus hy over all points xy in S. Our goal is to find an optimal solution that we're going to denote by x star, y star, and we're going to denote by z star its optimal value. Our point of departure is the natural linear programming relaxation. This is a linear program obtained from the original integer program by dropping the integrality constraints. So it's the problem of maximizing cx plus hy subject to xy in P0. As we have seen in the previous section, P0 is the natural linear relaxation of S obtained by replacing Zn plus with Rn plus. So now let's say that we have solved the natural LP relaxation and we have an optimal solution that we denote by x0, y0, and we also have the corresponding optimal value z0. So now, how can we use this natural LP relaxation? The first question is, how does z0 compare to z star? Well, it is simple to see that z star is less than or equal to z0. This is because the linear program and the integer program have the same exact objective function. But the linear program has a feasible region that contains the feasible region of the original integer program. Therefore, in the linear program we are maximizing the same function over a larger set. And so the optimal value will be greater than or equal to the optimal value of the integer program. The second question that we pose is, what do we know if x0, y0 has x0 integral? Well, in this case, the optimal solution to the linear program is also feasible for the original integer program. The point x0, y0 is the best point among all the points in P0. Therefore, it's also the best points among all the points in S because S is a smaller set. Therefore, if we know that x0 is integral, then x0, y0 is an optimal solution not only of the linear program, but also of the integer program. And so we can say that z star is equal to z0. So if we solve the linear program and x0 is integral, we are done. We have solved also the integer program. Therefore, we now focus on the case where x0 is not integral. Now let's discuss the branch and bound method, and let's see what it does in the case where x0 is not integral. Branch and bound consists in a way of two separate ideas, branching and bounding. So let's start with branching. The idea of branching is to divide the original problem into subproblems. Since x0 is not integral, we can pick an index j such that x0j is fractional, and we denote this fractional number by f. Now we define two new mixed integer linear sets, starting from the original mixed integer linear set S. The first one, S1, is obtained by adding to S the linear inequality xj less than or equal to the floor of f, while the second one, S2, is obtained from S by adding the linear inequality xj greater than or equal to the ceiling of f. Now, since xj is integer for every xy in S, we have that S1, S2 forms a partition of the original set S. Clearly, the next step is to consider the two corresponding mixed integer linear programs, one arising from S1 and one arising from S2. The objective function will be exactly the same original objective function of the original integer program. So in MILP1, we maximize cx plus hy over xy in S1, while in MILP2 we maximize Cx plus hy such that xy in S2. Clearly, the optimal solution of the original integer program is the best one among the optimal solutions of MILP1 and MILP2. So we just need to solve the two new subproblems. Now, in a way, this idea does not seem to be so smart after all. You can of course use it recursively, but at the end of the day, it is simple to see that you could simply be enumerating the original set S. But that's where the bounding step comes into play. This bounding step essentially allows us to turn this enumeration technique into a smart enumeration technique. Now, the idea of bounding is that in some cases we can discard a subproblem and not consider it anymore. So now let's consider the natural linear relaxations of S1 and S2 and the corresponding linear programming problems. So we denote by P1 the polyhedron obtained from P0 by adding the linear inequality xj less than or equal to the floor of F. And we denote by P2 the polyhedron obtained from P0 by adding the inequality xj greater than or equal to the ceiling of F. LP1 is then the linear program with feasible region P1, and LP2 the linear program with feasible region P2. Once again, the objective functions always coincide with the original objective function. Now we solve LP1 and we solve LP2. So let's consider LPI. There are of course several cases based on what the LP solver will return to us. So the first option is that LPI is infeasible, which means that the set Pi is the empty set. Since Si is contained in Pi, we can argue that Si is also the empty set, and therefore MILPI is infeasible. In this case, this subproblem is discarded because it is infeasible, and we say that this subproblem is pruned by infeasibility. In the next case, we have that the LP solver returns an optimal solution of LPI, and we are going to denote it by xi, yi. We also denote by zi the objective value of xi, yi. Now we consider three different cases. The first case is when xi is integral. Well, in this case, as we have seen, xiyi is an optimal solution of MILPI as well. In this case, we have found the optimal solution of the subproblem, and so we say that this subproblem is pruned by integrality. In this case, the vector xiyi is optimal for MILPI, but of course in general this will not be optimal for the original integer program. However, it is for sure feasible to the original integer program. Therefore, we can argue that the zi is less than or equal to z star. In other words, we have obtained a lower bound on z star, and this lower bound is precisely zi. In the remaining two cases, we assume that xi is not integral. Let's first consider the subcase where zi is at most the best known lower bound on z star. This means that no feasible solution of LPI has objective value better than the best known lower bound on z star. Therefore, no feasible solution of LPI is better than the best feasible solution of the original integer program found so far. Since Si is a subset of the feasible region of LPI, this implies that Si cannot contain a solution better than the best feasible solution for the integer program found so far. Therefore, we can discard this subproblem and we say that it is pruned by bound. The only remaining case now is if xi is not integral and zi is greater than the best known lower bound on z star. In this case, this subproblem may contain an optimal solution to the original integer program. Therefore, we cannot prune it. What we do instead is recursively apply everything we've done so far. Since xi is not integral, we pick a fractional component of xi. Let's say that this fractional component is xi j prime, and let's say that it is equal to f prime. Then we can define a partition of Si into Si1 and Si2, where Si1 is obtained from Si by adding the linear inequality xj prime less than or equal to the floor of f prime. And Si2 is obtained from Si by adding the constraint xj prime greater than or equal to the ceiling of f prime. And at this point we can simply repeat the whole process. Now let's see a simple example. This is the same example that we have already seen previously, and in particular it is a pure integer linear program, so both variables are integer. What we're going to see in this slide is a complete run of the branch and bound algorithm. For each subproblem that we're going to consider in the branch and bound, I suggest that you also visualize the corresponding feasible region to get a better idea of what's going on. So, in our first iteration of branch and bound, we solve the standard linear programming relaxation of our integer program. We obtain an optimal solution that is 1.3 and 3.3, with objective value 14.08. The optimal solution of the LP that we have found is not integer. Therefore, we choose one of the two components that is fractional and we branch accordingly. For example, we could choose x1 since it is fractional. The value of x1 is 1.3, therefore we branch in the following way. x1 less than or equal to the floor of 1.3, which is 1, and x1 greater than or equal to the ceiling of 1.3, which is equal to 2. Let's first look at the subproblem on the left. We now solve the linear program obtained from the previous one by adding the inequality x1 less than or equal to 1. The optimal solution that we find is x1 equal to 1 and x2 equal to 3, and the objective value of this solution is 11.8. Note that we have found an integer optimal solution of the linear program. Therefore, we can prune by integrality. In particular, we have found now our first lower bound, which is 11.8. Now we focus on the remaining subproblem. We solve the corresponding LP. This is the linear program obtained from the natural linear programming relaxation of the original integer program by adding the inequality constraint x1 greater than or equal to 2. The optimal solution that we find is 2, 0.5, with objective value 12.05. The solution found is not integral, so we cannot prune by integrality. And the objective value, 12.05, is larger than the best known lower bound, 11.8. Therefore, we need to branch again. The second component of our optimal solution is 0.5. Therefore, let's branch on x2. We then generate two subproblems. In one, we add the constraint x2 less than or equal to the floor of 0.5, which is 0. And on the other one, we add the constraint x2 greater than or equal to the ceiling of 0.5, which is equal to 1. Let's consider first the subproblem here on the left. This is the linear program obtained from our original natural linear programming relaxation by adding the two constraints x1 greater than or equal to 2 and x2 less than or equal to 0. The optimal solution that we find is 2.125, 0, and the objective value is 11.6875. The optimal solution is not integral, so we cannot prune by integrality. However, the optimal value is strictly smaller than the best known lower bound, which is 11.8. Therefore, we prune by bound. At this point, the only subproblem left is the one down here. We solve the corresponding linear program, and our solver tells us that this is an infeasible linear programming problem. Therefore, we prune by infeasibility. We have now explored all the subproblems in our branch and bound tree. Therefore, we conclude that the optimal solution of our integer program is 1, 3, with objective value 11.8. In the branch and bound method, there are several choices that we make, and specifying different ways of taking these choices will result in different algorithms. For example, so far, we use a specific way of branching and a specific way of bounding. For branching, we used what is called variable branching, where the branching step creates two integer programs, subproblems, obtained by restricting the range of a single variable. For bounding instead, we used linear programming, where in every node of the branch and bound, we solved the natural linear programming relaxation of the integer program corresponding to that node. It is simple to come up with different ways of doing both branching and bounding. However, the strategies that we just discussed are probably the simplest one, and they are also very effective because they are widely used in state-of-the-art integer programming solvers. Next, I want to formalize for you the branch and bound with linear programming bounding. In particular, the algorithm that we will see is a bit more general than what we have seen so far, since we keep using linear programming bounding, but we don't use variable branching. So I want to write a full algorithm for you. In this algorithm, we will keep a list of linear programming problems obtained by relaxing the integrality requirements and imposing linear constraints. And every LP of this form corresponds to a node of our enumeration tree. Now we need some notation to properly state our algorithm. We're going to denote a node of the enumeration tree by Ni, and the corresponding linear program will be LPI. We will also denote by Zi the optimal value of LPI. The node N0 will be associated with the natural LP relaxation of the original integer program. The list of nodes that still are unsolved will be denoted by L, and the currently best known lower bound on the optimum value Z star will be denoted by Z bar. Now we can write our branch and bound method. It consists of 6 steps. In step 0, we initialize L, Z bar, and X star, Y star. L contains only our initial node N0. Z bar is set to minus infinity because currently we don't know any lower bound on Z star. And we set X star, Y star to be the empty set. Throughout the algorithm, in X star, Y star, we will record the best feasible solution found so far, which is precisely the one with objective value Z bar. Step 1 is our termination check. If L is the empty set, all the nodes have been solved and therefore our current best solution, X star, Y star, will be optimal. If this termination step is not triggered, then we have some nodes that still need to be solved. So we continue with step 2. In this step, we simply choose a node Ni in L and we delete it from L. The reason we delete it is because by the end of this iteration of the algorithm, we will have completely dealt with this node Ni. Step number 3 is bound. Here, we solve LPI, which is the linear program corresponding to node Ni. If it is infeasible, we prune by infeasibility. Therefore, we're completely done with this node and we go to step 1. Otherwise, our linear programming solver returns an optimal solution of LPI, which we denote by Xi, Yi. The objective value of Xi, Yi will be Zi. In step 4, we want to check if we can prune either by bound or by integrality. If Zi is less than or equal to Z bar, then we prune by bound, and so we're done and we go back to step 1. On the other hand, if Xi, Yi is feasible to our original integer program, then we have found a better feasible solution to the original integer program than the currently best known one. So we update Z bar and X star, Y star accordingly. So Z bar will be set to be Zi, and X star, Y star is set to Xi, Yi. In this case, we prune by integrality and we're done. Therefore, we go back to step 1. Otherwise, we go to the remaining step, step 5. We already checked whether we can prune, and we're in the case where we could not prune in any way, and so we need to branch. From LPI, we construct at least 2 linear programs, which we denote by LPI1, LPIK, with the smaller feasible regions, whose union does not contain Xi, Yi, but contains all the solutions of LPI with x in Zn. Next, we add the corresponding new nodes ni1 until nik to L, and we go back to step 1. Note that in this algorithm there are several choices that have not been specified and therefore have been left open. For example, the node selection in step 2. As you can see, here we didn't specify how to choose node Ni among all the nodes in L. And clearly, in the branching step, we did not specify how the linear programs LPI1, LPIK should be constructed. In a way, the most fundamental feature of branch and bound is its ability to prune the tree. Essentially, every time you prune the tree, you get rid of a part of the feasible region, which therefore you will not need to enumerate. So it is of fundamental importance the ability to prune the tree as much as possible, which is done in step 4 of the algorithm that we have just seen. In particular, we prune by bound when zi is less than or equal to z bar. Therefore, to prune by bound as much as possible, we want to make zi as small as possible and z bar as large as possible. In practice, good ways to obtain large values for z bar and therefore obtaining good lower bounds are obtained using heuristics. These are techniques that, in several ways, construct good feasible solutions to the original integer program. Generally, these heuristics have no theoretical guarantees on the quality of the solutions obtained. However, these solutions can be used in branch and bound to speed up the runtime of the branch and bound algorithm. On the other hand, to obtain zi as small as possible, so to obtain good upper bounds, it is important to formulate our integer program in a way that the value of the natural LP relaxation, z0, is as close as possible to z star. These simple observations give us some very good ideas on how to proceed with the research in integer programming. This course is theoretical in nature, so we're not going to talk much about heuristics. However, we will discuss much more how we can formulate integer programs in a nice way that gives us z0 very close to z star. To conclude with branch and bound, we have understood that there are 4 issues that need attention when solving integer programs with branch and bound. The first one is formulation, since a good formulation will give us a small gap z0 minus z star. The second is heuristics, which can be used to find a good lower bound z bar. Then there is the issue of branching, and to understand how to branch effectively. And finally, node selection. Which node should we pick among all the available nodes still unsolved? One very important technique to obtain good formulations is by adding cutting planes. Essentially, we add valid linear inequalities to our formulation to obtain a gap z0 minus z star smaller and smaller. In the next section, we are going to discuss the cutting plane method, which is based on adding these cutting planes. However, this cutting plane method has nothing to do with branch and bound. Later on, we will see how branch and bound and cutting plane methods can be merged to obtain what is called the branch and cut method, which is currently the best known technique to solve integer programs in practice. So now let's talk about the cutting plane method. Our initial setting is almost identical to the one we saw in branch and bound. We have an integer program, max cx plus hy subject to xy in S, where S is a mixed integer linear set. We want to find an optimal solution, x star y star, and the corresponding optimal value, z star. Once again, we look at the natural LP relaxation, which is the linear program obtained from the original integer program by discarding the integrality constraints. We now assume that we have a basic optimal solution, x0, y0, and we denote by z0 its optimal value. Now the key difference between this setting and the one in the branch and bound is that here we're assuming that x0, y0 is not only an optimal solution, to the natural LP relaxation, but also that it is a basic optimal solution, which means that x0, y0 is a vertex of P0. Recall that for a linear program, we can find in polynomial time not only an optimal solution, but also a basic optimal solution. So the assumption of having here a basic optimal solution is not really restrictive from a computational perspective. Now, in the cutting plane method, we're going to see a different idea for dealing with the case where x0, y0 is not in the set S. Here's again our running example. Now, the whole idea behind the cutting plane method is to find one new inequality, which we denote by alpha x plus gamma y less than or equal to beta, such that this inequality is valid for the set S and is violated by x0, y0. In our example, such an inequality could be the inequality x2 less than or equal to 3, which is visualized here. As you can see, it is valid for all the points in S, the black dots, but it is violated by the white dot over here, which is the vector x0, y0. We call such an inequality a cutting plane separating x0, y0 from S. Note that a cutting plane always exists, and this can be shown using the hyperplane separation theorem. We now define a new polyhedron, which is P1, obtained by adding to the polyhedron P0 the inequality alpha x plus gamma y less than or equal to beta. This new polyhedron P1 will be sandwiched between the feasible region S of the integer program and the polyhedron P0 of the natural linear relaxation. Therefore, the linear programming relaxation based on P1 is stronger than the natural LP relaxation. Note that we haven't defined what it means for an LP relaxation to be stronger than another one. We will give this definition later in the course, but for now let's focus on this setting, and let me explain what I mean with this. Clearly, the optimal solution x0, y0 of the natural LP relaxation does not belong to P1. Therefore, the optimal value of the new LP, with feasible region P1, is at least as good an upper bound on the value z star as z0. In other words, the optimal value of this new LP will be greater than or equal to z star and less than or equal to z0. In our running example, you can now check that an optimal solution will be this point over here, that is now a vertex of the new polyhedron. Now the cutting plane method is simply obtained by recursively applying this idea. So let's now state the cutting plane method. We're going to have a counter I that starts with I equal to 0, and we repeat the following recursive step. Solve the LP max cx plus hy such that xy is in Pi. Now let's look at the optimal basic solution obtained, which is xi, yi. If it belongs to S, stop, because we have solved the integer program. Otherwise, we solve the following separation problem. Find a cutting plane alpha x plus gamma y less than or equal to beta, separating xi, yi from S. We then define the next polyhedron pi plus 1 by adding to pi the inequality alpha x plus gamma y less than or equal to beta. And finally, we repeat the recursive step. Now we get back to our running example and just visualize how the cutting plane method could work on this example. The solution of the natural LP relaxation is this point 1.3, 3.3, and its objective value is 14.08. We now add the first cut, which is x2 less than or equal to 3. We solve the new linear program, and the basic optimal solution is now this vector here, 1.375, 3. The objective value decreased to 13.8625. We now add a second cut, which is, for example, x1 plus x2 less than or equal to 4. An optimal basic solution is then this vector here, which is 1.5, 2.5, with value 13.5. And you can continue in this way. If you're interested in understanding how these cuts can be generated, please look at our textbook. Anyway, later on in the course, we will thoroughly discuss how these inequalities can be generated. Now, in the cutting plane method, the separation problem is the central issue. If the basic solution xiyi is not in the set S, there are infinitely many cutting planes separating xiyi from S. So one can ask several questions. How can we produce cuts? And how can we produce them effectively? On the one hand, one can look at the quality of the cutting planes obtained. And on the other hand, one can look at the computational complexity of obtaining such a cutting plane. And clearly there will be some kind of trade-off between the quality of the cutting plane and the time it takes to obtain it. Another interesting idea is that from one iteration to the next, instead of adding a single inequality, we could add several inequalities. So, like for the branch and bound, also in the cutting plane method, we came up with several interesting questions worth pursuing. And we will get back to several of these questions later on in the course. But now let's leave it at that, and instead we talk about the branch and cut method. As I already mentioned, the branch and cut method is obtained by merging the ideas in branch and bound and in the cutting plane methods. When we discussed the branch and bound, we saw that for being able to prune the enumeration tree often, we need a tight upper bound. This upper bound was the optimal value of the corresponding linear program. Now in the cutting plane method, we have just seen how tighter upper bounds can be obtained by adding cuts. Therefore, the idea of branch and cut is to obtain tighter upper bounds in branch and bound by applying the cutting plane approach to the subproblems. The resulting branch and cut method is currently the most successful method for solving integer programs in practice. What I want to do now is state for you the branch and cut method similarly to what we did in branch and bound. We are simply going to add a cutting plane step right before the branching step at the very end of the iteration. In this slide, in black, we have exactly what we already had in branch and bound. We have the initialization step, termination step, node selection, bounding step, pruning step, and right after the pruning step, we are at the point where we understood that we cannot prune the current subproblem, and this is where we add our new cutting plane step. In this step, we decide whether we want to strengthen the formulation LPI or we want to branch. If we decide that we don't want to strengthen the formulation, then we continue with the next step exactly like we did in branch and bound. On the other hand, if we want to strengthen the formulation LPI, we add some cutting planes and we go back to step 3. So once we have added cuts, we repeat the bounding and pruning step. The hope is that we are now able to prune this subproblem without the need to branch. Let's see more in details this step 3 and 4. Now the new LPI that we have obtained by adding cuts has a smaller feasible region than the original LPI. Therefore, it could happen that the original one was feasible and the new one is infeasible. So it is possible that we are now able to prune by infeasibility. If we don't prune, we denote once again by ISyE an optimal solution of the new LPI, and by ZI its objective value. Since the feasible region is smaller, the new ZI in general will be smaller than the previous one. Therefore, when we check whether ZI less than or equal to Z bar, it is possible that now this condition is satisfied while previously it wasn't. So it is possible that we now prune by bound. If we don't, it's also possible that the new solution ISyE is feasible to the original integer program. And in this case, we're pruning by integrality. So you see that adding cuts in step 5 gives us some hope that the new steps 3 and 4 could prune the current subproblem, which would allow us to avoid branching once again. The next obvious question is how can we decide whether we should add cuts in step 5 or no? Now there is no correct answer here. What I can tell you is that current state-of-the-art solvers take this decision based on the success of previously added cuts and based on some characteristic of the new cuts that can be beneficial for the solver. For example, cuts with few non-zero coefficients are generally preferred by solvers because they lead to faster computations. What happens typically in current state-of-the-art solvers is that several rounds of cuts are added at the root node n0, so at the very beginning of branch and cut. Later on, deeper in the enumeration tree, generally fewer or no cuts are added. One possible intuition behind this is that the cuts that are generated at the root node are then inherited by all the subproblems in the enumeration tree. On the other hand, the cuts that are generated in a node deeper into the enumeration tree are inherited only by the nodes below, and so in a way they will have less impact in the whole branch and cut procedure. And this concludes our preliminary discussion of the main techniques currently used to solve integer programs in practice. Several ideas that we have seen in this video will be the starting point that we will use to derive some very interesting theoretical results throughout the course.